Let us begin this lecture by looking at how rotation is actually measured. Consider the line OX1. With O fixed, we can rotate OX1 about O in the same plane as the computer screen. A rotation that takes OX1 back onto itself by turning through a full circle is a rotation of one cycle or one revolution. Thus, rotating OX1 anti-clockwise to position OX2 represents a rotation of 1/4 of a cycle, 1/4 of a revolution. Rotating OX1 again anti-clockwise to position OX3 represents a rotation of 7/8 of a cycle, 7/8 of a revolution. Measuring rotation in terms of fractions of a complete cycle soon becomes awkward. For example, which is the greater rotation, 3/13 or 13/53 of a revolution? If we want to quantify or compare rotations, it is far more convenient to measure rotation in terms of degrees or radians. A rotation corresponding to turning through a complete circle or one revolution is defined to be a rotation of 360 degrees or 2 pi radians. Those awkward fractions from the previous slide now can be quantified and compared. 3/13 of a revolution is 3/13 multiplied by 360 to give 83.1 degrees. 13/53 of a revolution is going to be 13/53 multiplied by 360 to give 88.3 degrees. If we want to measure those rotations in radians, then we need to multiply the fraction by 2 pi. So 3/13 becomes 3/13 multiplied by 2 pi to give 1.45 radians, 1.45 rad, and 13/53 of a revolution becomes 13/53 multiplied by 2 pi to give 1.54 radians, 1.54 rad. How to convert from degrees to radians and vice versa? We are going to use the definition that one cycle, one revolution, equals 360 degrees equals 2 pi. Dividing both sides of this equation by 360 gives us that 1 degree equals pi over 180 radians, which is approximately 0.017 radians. Dividing the equation by 2 pi gives us that 1 radian must equal 180 over pi degrees, which is about 57.3 degrees. Therefore, if we want to convert degrees to radians, we need to multiply the degrees by pi over 180. And to convert from radians to degrees, we need to multiply the radians by 180 over pi. How to calculate the length of an arc using radians? The diagram on the left shows a circular arc AB, which subtends an angle x degrees at the centre O of a circle of radius r. The diagram on the right is identical, except the angle theta is now a radian measure. Notice that the arc length is directly proportional to the subtended angle. If the angle at the centre, if the angle x is increased, then the arc length increased by the same proportion. Notice that the subtended angle and the arc length are directly proportional. If we increase the angle x to 2x, then the arc length increases from AB to 2AB. If the angle x degrees is increased to 360 degrees, then the arc length AB becomes the full circumference, which we know to be 2 pi r. This observation gives us the following pair of equivalent fractions. X over 360 equals the arc length AB over the total circumference 2 pi r. Therefore, if the subtended angle is measured in degrees, the arc length AB is simply going to be x over 360 times 2 pi r. If we measure the subtended angle in radians, then the pair of equivalent fractions are theta over 2 pi equals the arc length AB over the full circumference 2 pi r. Therefore, the arc length AB, if the subtended angle is measured in radians, is going to be given by the formula r theta. How to calculate the area of a sector using radians? The argument used on the previous slide is going to be used again. Observe, the subtended angle is directly proportional to the area of the sector. If the subtended angle is increased to 360 degrees or 2 pi radians, the area of the sector would become the area of the complete circle, pi r squared. Thus, if we work in degrees, we have the equivalent fractions x over 360 is going to be equal to the area of the sector AOB divided by pi r squared. Therefore, the area of the sector AOB is going to be equal to x over 360 times pi r squared. Working in radians, we have the pair of equivalent fractions theta over 2 pi is going to be equal to the area of the sector AOB divided by pi r squared, which gives us that the area of the sector AOB is going to be given by the formula a half r squared theta. How to find the area of a segment? We want to find the area of the minor segment that's been cut off by the chord AB. This area is given by the area of the minor sector AOB minus the area of this triangle AOB. We know that the area of the sector is now going to be given by 1/2 r squared theta. The area of the triangle is going to be half times the product of the two sides times the sine of the included angle. In this case, that gives us 1/2 r squared sine theta. Therefore, the area of the minor segment is going to be 1/2 r squared multiplied by theta minus sine theta.